Welcome, everybody. Thank you for being here and supporting this event. As Toby mentioned, my background was in the Navy, 30 years as a nuclear operator as well as a shipbuilder. But I'm super excited to be with TerraPower bringing nuclear power to the civilian maritime sector, because a long time ago, I went to the Merchant Marine Academy, and I still really like to see that we can apply this technology to the maritime sector. So as I think back on how I operated the naval fleet during my time, I look at those reactors that we operated, and as previously stated, those reactors, they're designed, they would be compact, they're designed to be operate on warships, they have to be very resilient, they have to survive extreme conditions, battle conditions, right? As we look at civilian reactors, right, the focus is a bit different in that they're optimized for long, steady power, safety, and meeting the regulations, the safety regulations that go with civilian power. So I'm very excited that we look at fourth generation reactor technologies and how can we now combine what we see is required for unique maritime conditions with that civilian concept of safety, security, and economic viability. I'm very pleased today that we have 4 leaders in advanced nuclear technologies with us here today. And I look forward to each of their presentations and hopefully some good questions and answers that this panel can answer for you about these technologies. First with us is Jeff Latowski, Senior Vice President for Molten Chloride Fast Reactor from TerraPower. TerraPower has been a trailblazer in developing new advanced nuclear technologies with their Natrium reactor as well as the Molten Chloride Fast Reactor. Next, we'll have Leah Kreider from Westinghouse. Leah is the Vice President for Commercial Operations for eVinci. Westinghouse clearly has a rich history in nuclear innovation and continues to push the boundaries with their eVinci microreactor technology. Joining us from BWXT is Joe Miller. Joe's the President for Advanced Technologies with BWXT. They clearly have extensive experience in naval nuclear propulsion as well as now small reactor technologies. So glad to have Joe with us here. And finally, from Idaho National Laboratories and the National Reactor Innovation Center, we have Nick Smith. Nick is the McCree Project Manager or Project Director at INL. INL is going to be instrumental in research and development of these advanced technologies to bring these technologies to market. Thanks for being here today. Jeff, we'll have you lead us off with presentations.
Let's use this one right now, right?
Yeah.
Great. Good morning. Thanks for having me. Looks like we're already on my first real slide, so I'll just jump in. We've been working on the Molten Chloride Fast Reactor at TerraPower actually since early 2013. Wasn't until late 2015 that we actually went public about that. That was part of, at the time, the Advanced Reactor Concepts program, where we had won an award with Southern Company as the prime, who's been our strong partner for over a decade now. Relatively recently, TerraPower has joined in as well and become a very strong partner, and that's now got to be about 4.5, 5 years at this point. So it's and then even more recently, Hyundai, who Mikhail mentioned just a few moments ago, they joined the team. And so we're very excited to have this group and carrying this technology forward, and I'll just share a little bit today about how we're doing that. On this particular slide, I just want to hit a couple of key features. Pieces of this Mikhail addressed. Just stand this way so I can see a little bit. But the inherent safety, actually, let me back up. Molten salt reactors in general, I think, offer a lot of flexibility and a lot of potential specifically for maritime. And that's tied in a number of ways to the fuel cycle and the ability to actually do some things with the fuel online. MSRs in general typically are thermal spectrum fluoride reactors, and they require a pretty heavy degree of online reprocessing. What works really well for us in the fast spectrum, and so it's the molten chloride fast reactor, so it's a chloride instead of a fluoride and fast spectrum instead of the traditional thermal spectrum. is the fission product poisoning is really much less important. And as a result of that, we don't really need to do as much to the fuel. And so we do a relatively light polishing. We filter it, as Mikhail mentioned, and we also have some gas sparging. And so certain things come out of the salt, but it's not real chemistry. It's not electrochemistry, it's not pyroprocessing, it's not some of the things that would raise more issues in safeguard space. This lets us have a long fuel cycle and treat this more like a nuclear battery. And it was mentioned, 10 years, 20 years, 30 years, we think those are doable. And so that's the big difference for a molten salt reactor and then specifically for the molten chloride fast reactor, that it helps in these ways. It's a less developed technology, and so we've been working very hard. And next slide, please. Shows a couple of the sizable programs that we've had over about the last decade. On the left side is the Advanced Reactor Concepts. We won that award in 2015, started work in 2016, and the culmination of that project, which ultimately ran about $85 million, the culmination of that was a machine grade out there called the Integrated Effects Test. All in, it's about a 7,000 square foot facility in our Everett, Washington laboratory, and has about 1 megawatt of electrical heating to simulate a nuclear environment. And this machine, which has a total of 4 loops, we're able to demonstrate some of the technologies. We're also able to work in thermal hydraulic space to make sure we're designing the codes, using the design codes properly to design the reactors for down the road. Very briefly, the program on the right, that's ongoing now. Ultimately, what we'll be doing in this, again, the culmination will become McCree, that was mentioned a moment ago, the molten chloride reactor experiment. That will be built in the former Zipper cell at Idaho National Lab, renamed Lotus. We'll use highly enriched uranium to actually keep the size very small. The core diameter is actually about this big. Kind of amazing, the wonders of HEU. To get to that point, there's a whole suite of separate effects tests, and culminating in a machine we call the McCree mock-up. So an electrically heated full-scale system that will be built with the real materials, and we'll field that again in the Everett, Washington laboratory. That will give us a platform to test out a lot of things. There's certain things you don't want to test, for the first time at Idaho National Lab with the world watching. You want to get these things done first to buy down the risk and speed up the time when you're in the cells at Idaho. So that mock-up again will be electrically heated and will also allow us to train some of the personnel and develop procedures for how we're going to operate this. Just pictures, a couple of pictures. We heavily believe in you got to build things. If you're not building things, you're certainly not credible. Strong list of partners. I don't have the time to go through here, but the integrated effects test itself is about 2,500 square feet, and there's about another 5,000 square feet dedicated to electrical systems, control room, and so on. But that's sitting in Everett. If you happen to be in town, you want to visit, let us know. And then, of course, this one's not built yet. This is McCree, but you get a sense of the sizing there. And again, a strong list of partners. I won't take the time to go through the parameters, but maybe if there's some interesting questions along those lines, we'll touch on that a little later. Again, we're in the middle of building things. The reactor head, some folks who have built large reactors will maybe get a chuckle. The reactor head for this thing is about the size of a large salad bowl. Again, HEU is a wonderful thing if you can work with it. We've recreated, in the lower right there you'll see, we've recreated the pit that we're going to find when we move the machine to Idaho. We want to be able to show that we can build the ship in the bottle, essentially, because it's a pretty controlled, limited space once we get there. But we have a whole pile of things that are in fabrication or even been delivered. So it's starting to get pretty exciting. And just wrapping up, on the left side, some of the thinking of what we're calling our minimum viable product. It's a little bit lower temperature, a little bit nearer term material selection. Ultimately, we think this leads to the demonstration reactor, which would happen in the early to mid 30s. And that would come in at about 180 megawatts thermal, 75 electric. And we think is suitable for first generation. Where we would be able to apply it to the maritime areas that were just mentioned, both propulsion as well as floating platforms. And I think for time, I'll go ahead and stop there and do the questions all at the end. Okay, thank you.
So I'm excited today to talk with you all a little bit about a different technology than what Jeff described. So here with Westinghouse, we're working on the eVinci microreactor. So I'm going to talk a little bit about that, about our terrestrial deployment model, some applications for this type of microreactor. I'll also show you some fun pictures of things that we're building, and then we'll talk a little bit about maritime. So for those of you who maybe don't live in the world of nuclear all the time, this term microreactor and small modular reactor, they sound really similar and they're not. Small modular reactors generally are around 300 megawatts. Microreactors are either less than 20 or less than 50, depending who you ask. They are also not all the same. So the eVinci microreactor is very different from other microreactors that are out there. Many of them have different ways of cooling, different sizes. So what I talk about with this one will be specific to ours, which is cooled with heat pipes. So it's a heat pipe reactor, makes 5 megawatts electric. If you're looking for more than 5 megawatts, we're happy to combine them. This goes with the concept that Mikhail was talking about if we can roll these out of our factory fully loaded with fuel, then it's good to be small and high in numbers. The way we cool with heat pipes, which I'll touch on a little bit, allows us to operate at near atmospheric pressure, and it means that we have a passive cooling system with almost no moving parts, which is important for safety. We also do not use water as a coolant. So for everybody who's been in there with those pressurized water reactors, we don't require that. So a little bit about how we think about operating in the terrestrial space. So it works very much like a battery, operates for 8 to 12 years, and during that time you don't touch it. So we bring it in, put it in one of these bays, get it set up and running. You can see that that's a pretty quick timeline. 7.5, 8 years later, we'll bring you a new one. We put it in the bay beside it, we wait until the first one is done, and then we just switch from one to the other and take away the first one. So very much a battery type of process, very little downtime between those. And they're built and fueled in the factory, take the whole thing away from the site. So you can think about how this might work in a maritime application in a very similar way, that you simply swap it out. You'll also see in this layout that there's no big containment building, no giant concrete structure. That goes back to the type of fuel that we're using. We use a type of fuel called triso fuel. It's a very robust form of fuel. It takes the uranium and encapsulates it inside of a ceramic. And that means that that ceramic is containing all of those things that we think about. That lets us avoid things like excavation and have a very small emergency planning zone, which is important for both terrestrial and any future maritime microreactors. So this is my nerd slide. I love my nerd slide, but I'll try not to spend too much time on it. We can always talk afterwards. Highlighting again the triso fuel that really builds the safety case here for being an inherently safe reactor, and the heat pipes. So the heat pipes, driven by natural phenomena, not requiring maintenance because there's not these moving parts or pumps or auxiliary systems. They also provide a great deal of redundancy. In our reactor, there's over 700 heat pipes, so should any one fail, you've still got over 700 taking heat out of the core. For those of you who live in the world of light water reactors, that means you can't really have a LOCA type of event. There's also no auxiliary systems that have to treat the coolant or do anything like that, which saves us on space and on complexity. So I will get off of the nerd slide on the next one. So a few application spaces that we think about are really where energy security is important to you. And that could be from sort of a defensive standpoint, but also if you own a manufacturing center and it costs you millions of dollars because your grid connection didn't work that day, thinking about vertical integration may be important to you. We think about off-grid and grid edge locations, particularly ones that may not have a lot of space available to them. We think about places that really need high reliability, high capacity factors where wind and solar type applications aren't going to cut it, but perhaps they are still interested in decarbonization. We think about space, which might seem a little odd, but it's a great application for nuclear power. Nuclear's been used in a number of ways. So we are working on 2 separate contracts, one for NASA to put power on the moon, and one for the Air Force Research Laboratory to put power onto satellites. So if we can do that, certainly we can put power in a port. I promised you some fun pictures on the next slide. So we're very much in a mode of build, test, and learn. You can see up here some testing that we've done recently at our new facility in Pittsburgh. So the heat pipes in that upper left corner, those are testing at full temperature. In the upper right is our control drum assembly. This is the primary means of controlling our reactor, so very important that we've assembled that and tested how it works. The lower right is the shutdown rods. Those are in during transportation and an emergency backup safety system. And then my favorite picture, decorated for Christmas, is our manufacturing demonstration unit. So that is a full circumference eVinci core using the same things we would use in the reactor in the field. So it's not mocked up, made out of aluminum and painted. That's real graphite there. It's very, very heavy. So in there you can see where the heat pipes would go, where the fuel would go, where those control drums would be inserted. Things that we can talk about progress on, we've recently had approvals on a couple of licensing topical reports from the NRC, so we're very excited to have approved things like our INC system and our principal design criteria for how the reactor will operate. All of these things up here and the work that we've been doing, we are planning for a test also at Idaho National Lab. I think you'll hear a common theme among all of us. We will be in the Dome facility, which is under NRIC's purview. On this next slide, this is our new facility, our microreactor hub in Pittsburgh, Pennsylvania at 51 Bridge Street. The pictures that you could see there, especially of the manufacturing demonstration unit, are from that facility. So you're all welcome to come visit, see some of the things we're doing, see how we're manufacturing heat pipes, get your hands on a few things, get them dirty. And on the next slide. So you may have seen earlier, we are working with TerraPower on a feasibility of how the eVinci microreactors can work in a floating nuclear power plant configuration. So thinking about how do we take these small batteries, put them on a ship, take them wherever they need to go, and deploy power that way. Really great application for places like ports. And if you want a small tug at your heartstrings, think about what you could do in terms of disaster relief and bringing in power that is reliable and easily set up. So we're really excited to continue that work. Happy to talk with any of you about it. And hopefully that is slightly under my allotted time today.
All right, excellent. Feels good to be back here in Texas. I moved to Texas 20 years ago to understand more about the high-tech manufacturing industry. I was focused on semiconductors at that point, but the 8 years prior was focused on naval nuclear propulsion and naval nuclear shipbuilding, both in shipyards in Newport News and serving on the USS Norfolk. In the 11 years since then, or actually the 13 years since I was here in Texas, I've been working at BWXT, focusing on everything that's new and different in nuclear, starting with small modular reactors, now focusing on microreactors, space reactors, and TRISO fuel that Leah mentioned. So to me, it's about what is new nuclear, how does BWXT use our heritage in manufacturing reactors, over 400 nuclear reactor deliveries for the Navy, for the commercial industry. How do we use all that to help what the future is? So there's a lot of future in maritime. Mikkel talked about it, Admiral Richardson talked about it. The future of maritime is focused on nuclear because of energy density. So how do we harness uranium-235? How do we get an energy-dense system into a commercial nuclear application? And how do we do it from proving that technology? So I'm going to talk a lot about what we've done as a company, what our focus areas are in microreactors, both for the Department of Defense. We're building that reactor now in Lynchburg. We're actually building 2 prototypes in Lynchburg. One for the Department of Defense, which is a microreactor fueled by TRISO. That demonstration will happen in the next couple of years, creating electricity in a full-scale demonstration The entire system, balance of plant, power generation, everything will be represented at the Idaho National Lab here in the next couple of years. So I don't have a lot of detailed pictures of that because of the application, because of the sensitivity around that application. But what we've done in parallel is we have started up a commercial variant of that reactor, and we've been working on that for 4 years as well, for commercial customers. So we have agreements in place with the Department of Energy to take that Pele technology, the high temperature gas reactor technology, and make it commercial for the industrial sector. We have a contract with the state of Wyoming. They're incredibly serious about using microreactors in the Trona Patch for mining and industrial applications. And we have another contract and actually an MOU with a variety of different customers and states and the federal government to make TRISO a commercial nuclear fuel. So we've been manufacturing that nuclear fuel for 20 years. It's been in use for 6 decades in a variety of different applications. So bringing all that technology and capability from BWXT, from my advanced technologies group, is extremely important to me. It makes me think back to why did I originally get out of nuclear 20 years ago? Because not a lot was happening. There's several of us that I keep in touch with from the naval program, from the commercial nuclear program, that went into other industries and now have come back to the nuclear industry. And we're doing that because it's real now, and we're building hardware. You saw some demonstration hardware from Jeff and Leah. We have our production hardware in our factories, over 4 million square feet in the United States and Canada, and we're going to bring that to bear to help all of industry and help our products and BWXT come to life. All right, next slide. So a little bit more about our history. 75 years of nuclear technology history, 160 years of BWXT history, formerly known as Babcock and Wilcox. So throughout our history, we've developed a variety of power generation products. Steam boilers was the genesis of our company, and taking steam boilers through every power generation industry is something that we have a claim to fame on, and focusing highly on nuclear over the last 10 years as BWXT, as the remaining company, named BWXT with a sole focus on nuclear, both in the commercial sector, making commercial nuclear fuel for the CANDU plants in Canada, and also services for a variety of different applications, and then the Naval Nuclear Program, running large nuclear laboratories, and then my group in advanced technologies. What you're seeing in one of these pictures is the NS Savannah. If you saw it in the hallway as you entered into this building, you saw the NS Savannah. That was a commercial nuclear maritime ship, reactor built by BWXT. And so when you think about the heritage of all of our companies and what we're doing now, you know, the history that we have and the outlook on the future, especially in maritime, is all well akin to making technology real. And we've done it in several different applications within BWXT. So these are the 2 microreactor projects that we have. Project Pele was launched in 2020. We went through a design competition for 2 years, and in 2022, we were awarded the contract to go off and build this reactor. We have over 3,000 components in Lynchburg. We've built a fueling machine that's shipping out to Idaho National Lab here in the next couple of days. The nuclear fuel is in manufacturing and will be shipped out by the end of the year. Core cartridge assembly is starting here in the next few months, where we'll take those 3,000 components that are going through quality verification now, put those into a format for the nuclear reactor, ship that reactor out to Idaho National Lab, and start making electrons again with new nuclear system. So it's all happening real time. Scaling that up to our BWXT advanced nuclear reactor is something that is extremely important for us, for the commercial industry, for the United States, for all industrial users that are interested in nuclear. So I talked about applications in Wyoming. There are applications here in Texas as well. I was here talking to ERCOT just a few months ago and talking about how new nuclear is going to become real in stages and how those stages can be utilized for public utilities and for energy security in the United States. So we have a 50 megawatt thermal reactor. That's the Banner reactor. We use a Brayton cycle, or we can use a Rankine cycle, depending on the application. For maritime, it would be the Brayton cycle. So being able to transport the thermal energy from the reactor to the power conversion system, we use a compressor. We use a couple of other moving parts, but it's really just 4 moving parts in the entire system will operate for several years without refueling. So the technology that you're seeing here on the screen from Pele to Banner has allowed us to fully understand what happens down to the material science of each one of the components inside of the reactor. Over the last couple of years, we've gone through a series of design reviews with the Department of Defense, with the Department of Energy, with the Nuclear Regulatory Commission to ensure that our design can operate, will perform, and will perform safely. And all of that is coming to bear here in the next couple of years in our demonstration for Pele. So that institutional knowledge, the supply chain that we've built up for this high temperature gas reactor, the licensing basis for this high temperature gas reactor, once again, is all being focused on Pele, and all of that institutional knowledge is being transferred to our commercial variant called Banner. So over the course or across the spectrum of power needs and power output, this is where we see Pele. It's really small packages, right? 1 to 5 megawatts. Put these reactors in a series of Connex boxes, ship those Connex boxes worldwide, allow power on demand to occur, allow the power density and the volume and mass constraints of a tactical machine for the Department of Defense is at the low range. Utilizing that technology once again in Banner gets you to the medium range, to the 15 megawatts thermal. It's larger in diameter than Pele, but also very factory manufacturable. We'll go on site. It's a similar diameter to other high temperature gas reactors that are out there, and we get the performance that we need out of this reactor based on the core physics that we've defined, and then the performance that we need in a commercial setting based on the selection of the balance of plant equipment. Just very specifically, do we use a steam boiler? Do we use a gas-to-gas power conversion system? Just depends on application, but that's really the alterations and the customization that we need to make in this reactor for a variety of industrial sectors. So TRISO fuel, Leah talked about it. TRISO fuel is extremely important because the emergency planning zone, because of the safety basis, because of the encapsulation of the fuel is allowable by manufacturing a fuel in this format. So what you're seeing on the right side of the screen are compacts. Those are uranium, high-assay LEU compacts manufactured at our facility in Lynchburg, Virginia. Those compacts start off as a TRISO kernel. The kernel is coated several times. It is put into compact form by using a very simple manufacturing process. It's inspected and it's put inside of the reactor. It's really quite that simple. And what you're seeing on the bottom left is what each one of the TRISO kernels looks like. It's about the size of a ballpoint pen or a poppy seed. And then on the top left is our manufacturing facility. So in Lynchburg alone, we have over 1 million square feet of manufacturing dedicated to building reactors. We ship at least 2 every year out of that facility, and we've been doing that for several decades. And what we're looking to do here in the next couple of years is ship this TRISO to the Idaho National Lab, insert those compacts inside of our Pele reactor, and then operate and prove the technology. Now, different from Banner, where we have a very specific technology that's being built by BWXT and shipped to our customers, TRISO fuel is for every reactor provider, right? So we're going to commercialize reactor. It's, pun intended, rising tide lifts all boats, right? And I think that's really important for us because we have the capability to manufacture this fuel. We're very interested in making sure this fuel is available to all the customers and the timelines that they need that, and kickstarting the industry with this fuel for terrestrial and potentially maritime applications in the future. And this is what we've done so far. Working with Crowley, we've designated a few different variants of barge power units for Banner and how we can use the Banner reactor to put on a barge, much like what Mikhail talked about with shore power coming onshore from these units. And so in that process, what we have done is we've gone through a thorough evaluation of how a high-temperature gas reactor, using a Brayton cycle, using that Brayton cycle to generate electricity, and how we can integrate that into a maritime application. So it's the combination of system knowledge from the reactor plant, the maritime knowledge, the barge knowledge that Crowley has, and allows us to make parallel developments with not just developing this reactor and fielding this reactor for proof of concept, but also applying this reactor to a maritime or barge-mounted operation. All right, good. With that, I'll turn it over to Nick. Thank you all.
My name is Nick Smith. I work at Idaho National Laboratory. I'm the project director for the molten chloride reactor experiment, and I've been there for about 5 years. Previously, I was the deputy director for NREC, and so I'm still very excited about all the NREC projects we have going on. I want to talk about some of those today. You know, the thing about Idaho National Lab is that every reactor in operation today traces some part of its DNA back to the 52 reactors that were built at the National Reactor Testing Station. And this is why I took the job at INL. It's why I moved my family to Idaho Falls, because it's a special place. You can do things at this site that you can't do anywhere else in the world. The timing is right, the excitement, you could just feel it all around nuclear right now. There's so much more to do in this nuclear space. So just looking at the history here, peak of the test reactors that were built during National Reactor Testing Station was like 26 reactors. This is Eisenhower administration. We were building multiple reactors a year, turning them on, testing a specific thing, and then decommissioning them quickly and turning around and doing the next one. And this is where, the nuclear navy was developed. This is why we have a commercial nuclear power sector. This is where the whole field of nuclear medicine comes from. We went through a little bit of a lull in nuclear in the 90s. Idaho National Lab definitely felt that. You talk to people that have been there the whole time, and they'll tell you it felt like it was just waiting to die, for every project to be decommissioned, cleaned up. There was no excitement for new nuclear projects. And all of a sudden, really in the last 5 to 10 years, the tides have turned. Everyone realizes this is the future. This is the most powerful energy source we've ever gotten to work, and we've got to utilize it to power our economy. So, you look around the field, and there is so much excitement there. It's an incredible time to be in nuclear. We've got test beds being developed at INL so we can help expedite people getting their reactors to market. We've got new small modular reactors, new micro reactors, commercial deployments that are underway, under construction, fuel being produced. It's just, I don't want to go through this whole slide because it would take too long, but you could see there is a tremendous amount of energy and investment going into this now. So I wanted to highlight kind of the key projects for INL right now. The first one is the DOME testbed. So it's demonstration of microreactor experiments. And, we're really excited to be working with Westinghouse on the feed project there. Hopeful to get that, first operational contract going. We've got the Lotus testbed, which is laboratory for operation and testing in the U.S. So this is a lower power testbed that enables you to work with things like highly enriched uranium, potentially plutonium. Maybe somebody's got a neptunium reactor they want to test. We'll bring it over. We can test it in there. And then I guess, the other pieces of this would be the Pele project. I definitely Justin Coleman's my peer who leads the Pele project, and spend a lot of time, hanging out with him, talking about how efficient all the government regulations are. That's a joke. I don't know. We also talk a little bit of trash, who's going to get online first. I think it's a healthy race, they're a healthy dynamic, but we're excited to have the Pele reactor coming to Citric. Already broken ground, actually constructing the site where it's going to operate. So it's just really cool to see that happening. And then we're also looking forward to the Oklo Aurora reactor. I personally, we can go to the next slide here. I personally am most familiar with, we'll stay here for a second, the DOME testbed. I guess one of the things I wanted to highlight is a change in philosophy I think you've seen over the last 5 to 10 years really. And instead of companies trying to demonstrate their first commercial version of their reactor without going through discrete stages of scale up, I think there's a willingness to have sort of these smaller prototypes that can be demonstrated in a facility that has a multi-unit life to it. So the DOME is a perfect example here. If every company had to do a microreactor, get the NEPA siting approvals and build this huge concrete shielded structure, and it's a big loss leader before you actually get to a commercial product that makes money. And so being able to share that infrastructure, I think is going to help a lot. It lowers the barrier to entry to get those first kind of experiments and test runs done. But Lotus is a similar concept, just lower power. The first reactor that's going to be in there is going to be McCree, the molten chloride reactor experiment. And I am partial to this one because it's what I work on almost every day. But it's an exciting time to be at the lab. This project, it's really a unique place to be able to do this. When we first started considering doing an HEU fueled reactor, everybody I talked to was like, they're never gonna let you do that. You better not even ask, or you're gonna get in trouble. And I asked anyways, and then it ended up working out for us. But I look back at the history of these reactors, and every single reactor that was built during National Reactor Testing Station, without exception, was HEU. Now, that doesn't mean we need to go commercialize a bunch of HEU reactors, but it significantly simplifies things for first-of-kind tests. We have a partnership between Southern Company, TerraPower, INL, Core Power, and really TerraPower is responsible for designing the reactor, fabricating it. They're going to bring it to INL. We're going to install it in the test bed. And INL is responsible for making the fuel. So let's talk about making the fuel. This is the most significant fuel production effort INL has undertaken since 1960 when EBR-2 was coming online. We are making more than a metric ton of fuel for this reactor, HEU fuel, with a process that we had only demonstrated at the 20-gram scale when we committed to the proposal for this project. There's been challenges. The chemistry for making fuel salt is not as simple as you might have hoped. There's easy ways to do it at small scale, and then you get to scaling up to 9 kilograms of uranium a batch, and it surprises you on what little mechanical, organizational, how to get the process to run to completion. This team has done an incredible job. These are our 3 fuel salt chemists who have, there's nose prints and forehead prints all over the glove box glass in there from late nights working to get things done. The salt is heavy. They're reaching in there with their gloves in there. Anyways, go to the next slide here. We're on track to complete our fuel synthesis, our first batch of HEU fuel synthesis this summer. So the fuel synthesis line is almost complete. It'll be done this summer. I'm not going to go down to the list of all the different pieces on this, but we're involved in every aspect of the engineering for the McCree project. We come across a safety question, we got to go back and do an experiment to dig in a little bit and see what's the right answer, how we're going to approach this from a DOE authorization standpoint. We've had to order a lot of hardware. It's all showing up now. Probably the thing I'm personally most proud of on our list of accomplishments here recently is our technical and functional requirements for bringing a nuclear reactor into a DOE authorized facility. It's 350 pages of nitty gritty, down in the weeds. These are the technical requirements, and nobody had ever consolidated all that information into one place before. So team who did that, they did an incredible job. Anyway, I'll stop here. I'm probably over time, but thank you.
All right, great. We have opportunity for questions for this panel. So we have a couple microphones that are out in the crowd there. So if you would like to ask a question, if you please raise your hand and we'll get a microphone to you. There's one right there in the back, Aaron.
Joe, this is Rod Adams. Used to work at BWXT. I think we were colleagues at one point. Quick question for you on the TRISO fuel. It's often described as the most robust fuel. Some people also describe it as the most expensive fuel. Do you see a learning curve as you scale up manufacturing?
Hey, Rod, good to see you. Yeah, absolutely. So we've been manufacturing the fuel at industrial scales, but not at mass production scales. And like everything else, we definitely see a learning curve allowing us to drop the fuel price over time. And we've gone through an evaluation of the supply chain. We've gone through an evaluation of what the real customer order book would look like. And we see that dropping. It harkens back to my experience in manufacturing semiconductors. That's a lot more intricate than making TRISO fuel. And the cost drivers for semiconductors, as we all know, has gone down substantially. So when you think about something like that has quality requirements based on performance, and quality requirements for nuclear fuel is similar. Performance and safety is there. So as we go through scale up, we've been very focused on pinpointing the exact development activities that give us the most bang for our buck to reduce cost and increase throughput, which are closely coupled, as you know. So I see a dramatic reduction in TRISO, but it's going to be based on the true order book of TRISO as we move into the future.
Okay, a question up front here. Anyone else on the way? Oh, I think one on the way.
Alberto Morandi with NOV.
Oh, got one up there, then we'll go to you.
I'm sorry. I have a question for Jeff. I mean, you mentioned demonstrator middle next decade, right? And TerraPower was formed in 2008, so it's like a 25-year journey, and you guys building things. But against that, how do you see the timeline of this actually being deployed commercial scale for maritime?
Yeah, that's working. TerraPower started work on, at the time, the traveling wave reactor, which is a sodium fast reactor and has become natrium over time. That began in the early days. The molten salt work didn't start until I arrived in mid-2012 and basically came upon the MCFR in early 2013. By the end of 2013, we were making uranium salts and actually testing them, playing around with them to see what we thought. So yeah, it's been a decade. It hadn't been 15 years yet, but and I'm sure the next decade will go really fast. An aggressive scenario has our demo turning on in 2034. So we got another decade to go.
Okay, up front here.
Long way to go. Hi, I'm David Cole. I came in from Atlanta, Georgia. Even with Vogtle 4 up and operating, we're still 3,000 megawatts in the hole. And I've got sites. That's why we're here. I've got sites, and we've got data center developers. They're not asking for megawatts. They're asking for gigawatts. We don't have any power. We buy our power from Mississippi and Florida to supplement the power generation. We've just shut down 2 coal power plants, and there doesn't seem to be a strategic plan to provide the energy that we need. I've got data center developers. I've got 2 hydrogen plants that require an enormous amount of energy, and I've got a site, but I don't have site selection criteria or restrictions. Is there or are there restrictions for your development where what do we do to confirm that we can drop your SMRs on our site to power our data centers, to power our hydrogen plant? Oh, and also, we're helping support Hyundai's new automotive plant, which will soon be producing long-haul hydrogen tractor trailers. And we don't have any hydrogen. We've got to produce it. And the one hydrogen plant we have in Georgia produces 30 tons and has a 180 megawatt substation requirement for it. So if that's giving you some idea of scale of power demand that we need right now, we need every bit of everything you're describing, but we don't have site selection criteria or restrictions to determine where we can put them. Are there restrictions for your SMR development?
So lots of demand out there as you're identifying, and question, I guess, to the panel on site selection criteria and how that can be developed.
So it's all part of the siting and regulatory process, right? So there's been a tremendous amount of success in Georgia over the last couple of years with Vogtle 3 and 4. So that's something that you can use as a launch point for your site. If you're looking for gigawatts, microreactors aren't really the best use case for that. It would be, let's keep building nuclear power plants at larger scales, the gigawatt scale plants. So I think it just goes back to their site-specific criteria based on the geology and the environment, but then we can form that up with a regulatory process for a variety of different microreactors or larger reactors.
So I'll build on what Joe said, which is these technologies are all different from each other, so everybody's siting requirements are thus gonna be different from each other. If you bring it back to maritime, it's, a yacht and a sailboat don't need the same things. So I think if we look at the situation you're describing, you need a nuclear all of the above approach. So from a Westinghouse perspective, on the gigawatt scale side, we've got an AP1000, that's got its siting criteria. We've got a small modular reactor in the AP300, slightly less restrictive siting criteria. And then something like the Avenchi, which has siting criteria, but they're more akin to like, are you on an active volcano? No? Okay, you're probably okay. So I think in these different application spaces, you might find, hey, a microreactor is great for the automotive plant, but for the 3 gigawatt data center that somebody wants to build, then it's probably a different technology in a different location. So I think you're in a position where we've got to think about the specific application and then talk to the people who can provide for that application.
The only comment I'll make is just a plug for the other side of TerraPower. A Natrium reactor, might be a good start for you. They're building the demo in Wyoming, so that's probably more appropriate scale. Still, I don't know if you're going to build 3 to 5 gigawatts that you want to build a dozen of them. You may well want a larger light water reactor for that.
Up front here.
Hi, I'm Elliot Kennel from the Cameron Group. My question is whether we can safely assume that the PWR is not going to be a candidate for maritime reactors. I'm a high-tech guy, advocate of advanced technologies, and I have a little bit of a reputation of being able to predict the future, but I also picked Kansas City to win the Super Bowl. And so my question is, really? Is the PWR not going to be a candidate for a floating nuclear reactor?
So addressed earlier was some criteria that we looked at from Core Power's perspective on what is the candidate, right?
So I'm going to ask you a question back. PWR technology's been around for a while now. Why hasn't it already been adopted for new nuclear and maritime? You don't think the high pressure and...
Yeah, I think it was, and Savannah was also PWR, and naval reactors are all PWR. So I think it's about the commercial viability of licensing and insurability. It's something that Mikhail talked about as well. And when you look at the safety basis, especially for barge-mounted and then ultimately propulsion nuclear ships, it's going to be about what's insurable and what's going to provide the type of performance that you need. So that nexus right now looks like molten salt, high-temperature gas reactors based on everything that we've evaluated.
I think for those of you who may not know, way back in the 80s, Westinghouse licensed a floating power plant with pressurized water reactors in a joint venture. So it was licensed, but had some of these other commercial difficulties. I think the other delta that we've talked about with the PWRs is their use of highly enriched uranium. And that is a very big obstacle besides just the insurability and things like that, where we've moved research reactors off of them. I'm very impressed that INL is able to do some experiments, and I think that's great from a technology standpoint. But I think that the safeguards surrounding that would be more problematic than for the other lighter enrichment versions.
Okay, I think we've used our time here for this first panel. I want to thank everyone for participating. Thank you very much.